Okay, so I left you with a question. Why would we draw a PV diagram to display the Carnot cycle? Well, what does the area bound by a pressure with respect to volume curve represent? The integral of P with respect to V? That's work, right? That's work. So I'm doing an isothermal expansion, so I'm going to draw a line of constant temperature along here we'll call TH, the high temperature part of this cycle. And we're going to say we're going to go from a state 1 out here to state 2. Okay, and we're going to expand. We're going to increase our volume from a smaller volume to a larger volume. Notice what the area under this curve represents, right? Now I'm not going to fill the whole thing in. If you've got a pencil, I don't think I've got a pencil here. I do have a pencil. I don't think I've got an eraser. Nope. Alright, we'll do a pen. So I'm not going to fill this in all the way down. Okay, but notice this area all the way down represents potential work we could pull out of the cycle. Now, the next step, and again, this is where most of the work for the engine could potentially come from. This is potential work. All this area under this curve is potential work we could extract from this engine if we're operating a Carnot cycle. Step 2 is what we call adiabatic expansion. Now that's a really important word. If you don't know what that one is, you definitely need to pause and go look this one up in your notes or a thermo book. You need to know what that word means, adiabatic. I know we've not used it a lot, but it is really important for us. What does adiabatic expansion mean? Go look that up if you don't know and come back. Okay, so what does that mean? Adiabatic means no heat transfer. So we're going to expand this thing out just a little bit more, go to just a little bit higher volume, not a whole lot. Out here to state 3. Why the drop in temperature? Well, it's expanding and it's not really getting a chance to absorb or drop any heat. When you do that, it's basically boundary work kind of going on, and that means you're going to a lower energy state. Okay, so we're going to drop temperature to go from 2 to 3. Okay, so now I've got more area right here that I could potentially draw from. So I'm adding area. I'm adding a little more area right there. Okay, so the temperature here drops from TH to TL, which I've already drawn on my diagram here. And then we're going to go through an isothermal compression. Now we've already looked that word up. You remember that one, right? Isothermal compression. Into constant temperature compression. So we're going to move from state 3 at the largest volume, and we're going to move back. We're going to compress, go to a smaller volume to state 4. Now notice what's happened. I've added this area here because this is expansion, so that's positive boundary work. I've expanded it more, that's a little more positive boundary work. Now I'm compressing it. This is negative work. So I had all of this area was positive, but now I've subtracted this area off. Now if I'm doing this on the board, I color this whole area in, and then when I draw this line, I erase the area underneath because this is negative. This is positive because they're expansion. This is compression. This is negative work out. And then, right, so yeah, 3 to 4, okay? And then I'm going to go through a fourth process we call adiabatic compression. Adiabatic compression says that if I increase the pressure, decrease the volume a little bit, but mostly increase the pressure, what else is going to increase? Well, if this is a gas, that means the temperature is going to increase. Okay? So it's going to repeat. That's going to take me back to my initial state. And again, I've got an area bound by those curves. So this plus this minus that gives me an area. And the area equals the net work out for the cycle. I call this symbol a cyclic integral. Right? I've heard line integral used as well. A cyclic integral just means that the limits on this integral, right, are the same. It's a cycle, so it's saying we're integrating from state 1 to state 1 pressure with respect to volume. Okay, so go through an entire cycle. And how do we get through that cycle? Well, we go, and again, an integral is just simply the summation of a lot of little tiny things, little differential sized things. That's how we kind of need to think about that as engineers. We're not mathematicians. So an integral just means it's a bunch of sums of microscopic, tiny, differential sized things. So that means because it's a sum, I can break it up into its pieces, and so therefore I can break it up into the integral from state 1 to state 2, the integral from state 2 to state 3, 3 to 4, and then back 4 back to 1. Notice the sign on each of these integrals. Okay, this is expansion, this is positive. Okay. This is positive, this is positive, this is negative, this is negative. Compression indicates work done on the system. So if I'm calling expansion positive work and compression is negative, and what that means is expansion is positive, that means I'm calling compression negative. Because again, the original idea was this was for an engine. And for an engine, you want to get work out. That's your goal. That's the positive quantity. Okay, and so you can see here, this is the process. To maintain a constant temperature during the expansion, you've got to add heat. So here's where you're dumping heat in at the high temperature. And down here, to maintain constant temperature during the compressions, from 3 to 4 is isothermal compression. So to maintain a constant temperature, you have to reject the heat. It doesn't get turned into work. You have to reject it here from 3 to 4. You reject that at the low temperature. And again, the area bound by this curve represents then the net work that you can get out of this engine. That's pretty cool. Okay. Now, we don't have anything that operates in a Carnot cycle. The closest thing we could maybe think about is using a piston cylinder that we expose to a high temperature heat source and allow it to absorb heat while it expands, and then insulate the whole thing, remove the heat source, insulate the whole thing, and then allow it to expand a little more, and we go to a lower temperature state, and then we compress it while we allow it to lose heat at the low temperature, and then we compress a little more to get it back to we insulate it completely and compress it just a little bit more. So that's kind of a graphical representation. We don't really have anything that does this. Stirling engines kind of, but yeah. Anyway, so again, Carnot, when he proposed this cycle, he said, look, all of these, if we could do these where they're all reversible, then that would be the best possible scenario. Okay, and so since they're all reversible, notice what happens when I run the reverse. Okay, so if I reverse this cycle, so now I go this way, and this way, and this way, and this way. Well, I still have a low temperature down here and a high temperature up there, but I've changed the direction that the heat flows. This is what we call a refrigeration cycle, the Carnot refrigeration cycle. If I run the thing in reverse, well, now I'm compressing, now I'm expanding down here, and I'm expanding, and then I'm compressing and compressing, which is essentially what a refrigerator does. Okay, now, again, we don't have any refrigerators that operate in this fashion, but it's a neat thing to think about. Okay, so what that did, what does that do? Well, again, direct quotes mean these came straight from your book, unless I've quoted another source, and I'll give you the other source there. Your text, the Changle and Bowles text, says the efficiency of an irreversible heat engine is always less than the efficiency of a reversible one operating between the same two reservoirs. So what we're saying is that any heat engine you and I would build would be less efficient than the Carnot engine, because the Carnot engine is reversible. And by the way, any reversible engine that we could construct would operate more efficiently than our irreversible engine that you and I would go out and construct. And the efficiencies of all reversible engines then therefore must be the same if they're operating between the same two reservoirs. And so what that means is that the temperature of those reservoirs is the only thing that controls the maximum possible efficiency. Because if all reversible engines have the same efficiency, the only thing that's different or changes is the temperature of those sources. I know, that's a lot to process. And this is actually, if we accept the second law as true, this is actually really easy to prove, right? And so what that tells us is, and how we apply that, and again, it's real simple to prove this once we understand how entropy works. So when I do the exam 3 review, I'll prove this to you using the second law. It's real easy to do. It's not quite as simple to prove with other concepts, doable, but anyway. So what does that mean? This ratio of heat transfers is equal to the ratio of temperatures, the high and low temperatures. Now you have to use kelvins or Rankins. You have to use absolute temperatures there. Okay, common mistake. You have to use absolute temperatures there. But the efficiency, if it's the thermal efficiency of a heat engine, we established this earlier, is always, it's what you want, your output, the net workout, divided by what you have to do to get it, the heat in. And we said you can substitute in and get this down to where it's a function of the ratio of heat transfers. Well, now we're saying, look, we also can say, because the only thing that controls for a reversible engine, the only thing that actually controls the efficiency is going to be these temperatures. So the ratio of temperatures is equal to the ratio of those heat transfers. Now notice I want to make it very clear. I want to make it very clear. There's something here I am not saying. I am not saying that QH is equal to TH in no uncertain terms, and neither is QL equal to TL. This is heat, this is temperature. They cannot be the same thing, right? You can't convert kilograms to seconds, or you can't convert kelvins to joules. These are not the same thing. But we are saying the ratio of these two is equal to the ratio of these two if it's reversible. Right, so if I have a reversible engine, a Carnot engine by definition is reversible, and this ratio is equal to this ratio, and that means this efficiency then becomes the maximum efficiency, and we can determine that maximum efficiency as 1 minus TL over TH. And that sets the limit that we could expect for the efficiency out of an engine. And here it is here. And so if T is in Rankine or Kelvin, I've already stolen my thunder. Right, if T is in Rankine or Kelvin, then this gives us, this is the reversible heat engine thermal efficiency. This is the maximum efficiency for a heat engine. And we could write something very similar for the coefficient of performance for refrigerators and the coefficient of performance for a heat pump. But again, the whole principle here is that the thermal efficiency for any irreversible heat engine, anything you and I would construct, is always going to be less than the reversible one. The limit, this could be equal to if I have a reversible device. So the best possible scenario is it's equal to, but just about everything else is less than. Well, anything we're going to construct is less than. And again, similar concept, the ratio of heat transfers, if it's reversible, right, important note there, if I'm dealing with a reversible refrigerator or a reversible heat pump, then those expressions hold true as well. Okay? All right, not a bad place to stop. We'll pick up there on the next page.